So now we talked about enantiomers. In enantiomers also you have classification. So enantiomer or the isomer which rotates the plane polarized light towards the right direction are called dextrorotatory. Like if this is a plane polarized light and the isomer is rotating it towards the right, it will be known as dextrorotatory. Similarly, if you have an isomer and it rotates the plane polarized light towards the left direction, then that isomer will be called, or that enantiomer will be called levorotatory. Like there is a plane polarized light and the enantiomer has rotated towards the left direction. So it will be known as levorotatory. Now if you have a mixture of dextrorotatory and levorotatory in an equal amount, that mixture will have a zero net rotation and it will be called a racemic mixture. See, this is your plane polarized light. Let's say you have a dextrorotatory mixture. So the dextrorotatory mixture is going to rotate the plane polarized light by 60 degree towards the right. Okay, now this has done. Now you pass this plane polarized light towards the levorotatory mixture. When you pass this towards the levorotatory mixture, this levorotatory is going to rotate this plane polarized light towards the left by 60 degree. So what we are going to get? We are going to get the plane polarized light back in the direction in which it was originally there. So you have zero net rotation and therefore 1:1 dextrorotatory and levorotatory mixture. 1:1 means they have equal amounts of present. It is called a racemic mixture and racemic mixture always has a zero net rotation. Now enantiomers have identical physical and chemical properties. That is their melting points, their boiling points, every physical and chemical property that you can think of, enantiomers have those identical. What they differ is in the direction in which they rotate the plane polarized light. That is the only thing which is differentiating them. That is the dextrorotatory and enantiomer rotates it towards the right and the levorotatory rotates it towards the left. So the one and only thing which differentiates the enantiomers, that is the dextrorotatory and levorotatory enantiomers, is the direction in which they rotate the plane polarized light. And rest all of the properties are going to be the same. This is not true for geometrical isomerism, by the way. For geometrical isomerism, cis and trans, if you talk about, cis and trans have completely different physical and chemical properties. Okay, everything you talk about, melting point, dipole moment, boiling point, cis and trans isomers will have everything same, which is opposite to that of enantiomers. So now how will you know if a complex will have enantiomers or not? If a complex will be optically active or not? All those complexes which does not possess or which do not possess a plane of symmetry will have optical isomer. Now what is the plane of symmetry? Plane of symmetry is like an imaginary plane that is passing through the molecule, dividing the molecule in half such that the half parts are mirror images of each other. Now let's see how the plane of symmetry is applicable or affects a molecule. Okay, so this is my molecule. Okay, you can see this is the molecule. You can imagine like it's BF3 or something. So this is the central atom and these are 3 atoms which are around it. So plane of symmetry is, as I said, it's an imaginary plane which passes through the molecule, divides it into 2 equal parts such that those parts are mirror images of each other. Imagine there is a plane passing through this atom, that is this white atom and this black atom. It's passing through this atom. What is that plane doing? It's bisecting this white atom and this black atom into 2 equal halves. Okay, so this is a mirror. Imagine that this is a mirror. Then you will be able to see that what is on the left side of the mirror is equal to what is on the right side of the mirror, right? This atom and this atom, they are going to mirror each other. This part of this atom is going to mirror this part of this atom, and this part of this atom is going to mirror this part of this atom. That is what a plane of symmetry is. Okay, there are other planes of symmetry also in this. So let's say I am putting this molecule like this and my plane of symmetry is going like this. Okay, it's going from here. So what is that plane of symmetry doing? It's bisecting all the atoms into half. So if it's bisecting all of the atoms into half, then this part, the above part of this atom is going to mirror the below part of this atom. The above part of this atom is going to mirror the below part of this atom. Similarly, the above part of this atom is going to mirror the below part of this atom, and the above part of this atom is going to mirror the below part of this atom. That is, this is the plane. Okay. So all of those compounds which possess a plane of symmetry, even if they possess one plane of symmetry, this I gave you an example, it possesses two planes of symmetry. Okay, first I cut it like this, then I cut it like this. So even if a molecule possesses one plane of symmetry, then also it's going to be optically inactive. So the criteria is, how is a molecule going to be optically active? It does not possess any plane of symmetry at all. Okay, so now we have a kind of set of rules. You cannot say it's actually a set of rules, it's actually a set of facts. Okay, so from these you will know whether a complex is going to be geometric, is going to show geometrical isomerism or optical isomerism, or whether complex is not going to show geometrical isomerism and optical isomerism based upon that structure of the complex and based upon the hybridization of the complex. So the first rule states that geometrical isomerism is possible only in the complexes which have at least two different bond angles, in which one bond angle must be 180 degree. So if the complex does not possess two different bond angles, if it just has one bond angle, even if that one bond angle is 180 degree, okay, then also that is not going to have any geometrical isomerism. So the criteria is two different bond angles, one of which must be 180 degree. If in a complex the coordination number is 2 and the structure is linear, then the complex is going to have no geometrical isomers and no optical isomers. Coordination number is 2, that is means a metal, that is a central metal, is attached to two ligands and it is attached in a linear way. Now you have to remember about the rule that we previously studied. This is a linear molecule, okay, this is the central metal atom and these are two different ligands which are attached to the central metal atom. These can be same ligands too, okay, does not only necessarily mean that these have to be two different ligands. Even if these are the same ligands, then also geometrical isomerism and optical isomerism will not be possible. Why is geometrical isomerism not possible? First of all, because there is only one bond angle. This bond angle is also 180, this bond angle is also 180. Even if it's 180 degree bond angle, but still there is only one. So geometrical isomerism is not possible. And optical isomerism is not possible because this molecule is optically inactive. See, there is a plane of symmetry which is going through this side, which is cutting all the atoms in half and which is mirroring the above part and the below part. Okay, they are mirror images of each other. The above part and the below part are mirror images of each other. So this molecule is optically inactive. Even if these two, like let's just imagine that this is also blue and this is also blue, that is the ligands are same. If the ligands are same, then this will be a mirror, this will be a plane of symmetry also. So plane of symmetry is possible even if the ligands are different or even if the ligands are same. That means the coordination complex is going to be optically inactive no matter what the ligands are.